Institute. My name is Robert Hunt and I'm the Deputy Director of the Institute. It's my pleasure to welcome you here today. I thought I'd just start off by, if you'll indulge me for a moment, by explaining what the Newton Institute is. Our connection with Newton is simply that we're named after him and we all think he was a fantastic man. We don't actually study his life and works or anything like that, we just use the wonderful mathematics that he created. We're part of the University of Cambridge, but we're also the UK's National Research Institute for Mathematical Sciences. So mathematical researchers come to visit us from around the world and stay here for extended periods, sometimes up to 6 months, working together on topics that they find interesting, that they think are at the frontiers of modern mathematical research. And of course, they try to push those frontiers back. What we don't have is any undergraduate students. The Newton Institute, although it's part of the University of Cambridge, part of the maths faculty, which is just over there, we do not do any undergraduate teaching at all. Our role is purely to do modern mathematical research with the world's very best mathematical researchers. And we have one of them here today for your delectation. Professor David Banks is from Duke University in the UK, and sorry, in the US, and yes, well, you didn't know you'd moved, did you, David? In the US, and he's one of the organisers of a program that's running here called Statistical Theory and Methods for Complex High-Dimensional Data, which, as you know from the blurb for this talk, is all about understanding how you can discover structure in huge data sets. And there are many huge data sets that are kept by various organisations. And David's going to tell us a little bit today about how mathematicians are helping unlock the structure in those data sets. So over to David.
Thank you very much, Robert. As so often in my life, I must begin with an apology. I haven't taught a general class like this in forever. And so I have no idea if I'm going to get the level right. And I hope you'll bear with me as we try to move through this. For people who are fans of mathematics, I should pause and begin with that digression by pointing out that this is the room where Andrew Wiles 95, 98% proved Fermat's last theorem. So some of you may find that very gratifying. What I'm going to try and talk about are the statistical problems that are posed by large, high-dimensional data sets, sometimes not so large data sets. Oh, of course. Thank you so much, sir. Yes, I intend to talk about the problems that are posed by high-dimensional data sets, some of which are large, some of which are small, and I want to begin by talking about a linear regression model. Imagine that you are a bank officer and you have to decide whether or not to make loans to people who come in to apply for money. And one type of approach is to try and build a model that predicts how much money that person can repay, how solvent they are. In the loan application, the person provides you, the applicant provides you with a whole lot of information about them. Oops, that's not the right one. Yeah, never mind. In your loan application, you say how much money you make from your salary, how much money your spouse makes, perhaps how many years you've been employed by your company, perhaps how much money your parents have. Lots of things that allow the bank to decide whether or not you can repay a large loan or not. So one strategy for trying to use this multivariate information about your entire credit history to predict how much you can repay is to predict what's of interest, how much you can repay, as a function of your money, your wife's money, the how many years you've been in the job, whether you've declared bankruptcy, a lot of explanatory variables which are indicated by X. So all this information is from the dossier, and what the bank officer would like to do is predict the amount of the loan that can be given. And the weights, the betas, those are determined from previous loans and whether or not people repaid them and how it worked out. This is a linear regression model, and it's extraordinarily useful because it has lots of really good properties. one of which is it's highly interpretable. If the bank officer has to say, I'm sorry, Robert, I'm not able to make you your loan, well, I can at least tell him it's because you haven't been in the job long enough. If you come back in a year, then your credit record will have changed a little bit, and the fact that you've been in the job for an additional year will be sufficient for us to make the loan. Or we'll say, I'm sorry, Robert, you declared bankruptcy 4 times in the last 6 months. That makes it hard for us to give you a loan. You can explain why the decision has come out the way that it did. Another thing that's perhaps a little more subtle is that there is a large body of well-trodden statistical research that allows you to make inferential statements about the predictions here. If you say, I might be able to say, I'm 95% certain that you would be able to repay a loan of £20,000. I'm only 50% certain that you might be able to repay a loan of £100,000. You can make probabilistic statements about the amount of money that somebody can repay, and that's a very helpful thing that the linear model, the linear regression allows us to do. You also might think about interactions and transformations. Interactions arise from the fact that 2 variables are together informative in a way that a single variable, neither variable is singly. And I suppose one example of that might be looking at how smart you are and how many math courses you have taken. You want to try and predict how much somebody's net worth might be, and if you have how smart somebody is and how many math courses they've taken, well, there are a lot of very, very smart people who major in medieval French poetry. And sadly, they don't do so well in the economic rat race that is the modern world, and you see them sitting by the sides of streets, with begging hats saying, we'll translate Villanove's for money, or something like that. On the other hand, so being smart doesn't really scale very well with income. The number of math courses you take may not do very much to explain income either. But together, if you are really smart and you've taken a lot of math classes, then together that interaction between the 2 variables might say a fair amount about whether you're a prince of corporate industry or whether or not you are translating French poetry. So that would be an example of an interaction. Transformations. The natural scale of the variables may not be the most useful scale to look at. Clearly, if you're a loan officer, how long a person has held a job is probably very important. If somebody was hired last week, you don't really think that their background is strong enough that you can make a very large loan. If the person has been employed by that company for 20 years, this is a rock-solid income producer. They're obviously very stable. You can probably give them a pretty good loan. But the amount of money that you're willing to give does not increase linearly with the amount of time that they have been in the profession. Any time up to that first year and a half is probably all about the same. Anybody who's had the job less than a year and a half just doesn't look very good to a bank officer. After that year and a half, though, they begin to think, okay, you're a solid citizen, you make money. And the amount that they're willing to loan you increases, maybe roughly linear for a while, up until you've been employed for 10 years. After 10 years, the difference between another 10 years and another 20 years is almost invisible to the bank. The 10 years establishes that you're a solid income producer, and that's a good basis for assigning a loan. So what you have is a nonlinear relationship here. Something, oh, I'm sorry, that's the wrong one. Where's my eraser? There must be an eraser in this room. Does nobody in the Newton Institute make mistakes?
No, we don't. You have to write it out with your hand.
Okay, well.
Yes, there is one down the bottom there. Mike's just spotted. No, your right foot.
Oh,
Right foot.
I see, thank you. That would be the type of curve that you'd expect to see. Small changes in the first couple of weeks don't make any difference. Then there's this rapid increase after you've been employed for a reasonable amount of time, and then additional time on the job doesn't make you look like a better credit risk.
You've written on the vertical axis?
This is time, how many weeks you've been, and this one is your credit rating. Great, thank you. All right, there are other things, dummy variables, categorical information. You can look at what one's major was in college. That might be something that's informative about your credit worthiness. Whether or not you're married, that's another categorical variable that a bank officer might want to consider. So those are the types of things that are involved here. Computation is fast, and that turns out to be an issue in a lot of statistical applications later on. Furthermore, it's a very objective measure. In the old days, the bank officer looked you in the eye, shook your hand, and made a decision about whether or not he could trust you or not. And obviously that opens the door to all sorts of legal challenges nowadays. And so it's much better for the bank to have a formula that describes how creditworthy they think somebody is. And if that formula includes inappropriate things such as gender or race or whatever, then the bank is clearly in trouble. But as long as the formula is reasonable, then they have a defensible basis for deciding who gets a loan and who doesn't. Now, with that sort of platform, I just want to expand a little bit on some of the types of applications in which the hard stuff happens. The data mining issues don't arise so much in the context of creditworthiness. They arise in problems such as microarray experiments. A physician or a biochemist will take a tissue sample, some blood or some liver or some brain, and whip it all up and send it through a technological process that will determine which genes are sort of turned on in that tissue and which genes are not so active in that tissue. And so at the end of the day, you might have information on 25,000 different genes, whether they are ramped up as high as they can go and just producing like crazy, or whether they're essentially turned off or somewhere in between. And from that information, one would like to try and make some decision. Does this person have liver cancer? Does this person have some abnormal metabolic disorder? Is this person susceptible to lung cancer? Those would be the types of things that you'd like to try and understand. And it's very, very hard when you have 25,000 different explanatory variables and perhaps only a handful of people who have liver cancer and who don't have liver cancer. So that's one of the big problems in data mining, to try and find the best model, best predictions you can using a lot of explanatory variables, but not very many observations. Does that make sense to everybody? Okay, good. Another place where this might come up is a different version of this problem is in counterterrorism. I'm flying back to the United States on Sunday, so of course I worry if I might fit one of their profiles. They do have profiles that try and flag whether or not you ought to be allowed on the plane or not. And these things might include your nationality. It might include information on whether you studied at a madras. It might indicate whether or not you are somebody who voted against George Bush. There are all sorts of things that might be on their list of reasons not to let you on the plane. And you would like to hope that at least the profiling methods they use are not stupid. So what one imagines is that they go through a whole lot of data on terrorists and non-terrorists, and they try and find common patterns among the terrorists that distinguish them from the non-terrorists, and thus provide some credible basis for these secret profiling algorithms that are used. And obviously in this case, one problem is that there are just not that many terrorists out there, which is probably a good thing. But from a statistical standpoint, it's bad because it means that the quality of our profiling algorithms is probably very poor. Another issue is that there's probably a lot of error in the variables that we have on terrorists. They conceal their histories, and they change their names, and they don't say that they went to a madras. They say they went to Cambridge. And so you wind up with very peculiar sorts of error patterns in that, which makes it hard to do statistical inference. And finally, I have another example which has to do with the background level of cosmic radiation in the universe, which really thrills cosmologists, but it's perhaps a little technical. The main thing is it's a very nonlinear function of the part of the sky that you're looking at. And the bank loan officer that I talked about before was using a linear model. all of the terms entered linearly, a constant times an explanatory variable, plus a constant times another explanatory variable. If you have nonlinear relationships, it gets much more complicated, and that's a third type of problem in this business. Oh, yes?
Just one comment for some people in the audience. You didn't say too much about the outcome variable y. That's your dependent variable. And,
yes.
It's particularly because in the terrorism case, it's unclear that we have any measurements of y. Whereas in the bank, you can talk about the profitability of a class of loans presenting with the same covariance. And so there's a response variable. I wonder if you could just that might help some of the audience to understand how you're getting your formula or what it is that you're predicting.
Thank you, David. That's an excellent point. Let me bounce back to that. In the counterterrorism application, you actually have a lot of data on some of it. In some sense, Y is whether or not the person is carrying a bomb. And there are a whole lot of people who've gotten the plane and they're not carrying a bomb. Every now and then, very rarely, you get a little bit of data about somebody who gets on the plane with a bomb. And so you have this very asymmetric information flow, which is sort of what I was trying to express there. Now, you could imagine some other response variable than whether or not you have a bomb, whether you are, if you had some measure of how evil somebody is, that could be a response measure. But the number of bombs they've smuggled onto airplanes or the amount of money they've contributed to bad causes, those might be types of response variables that are sort of like a measure for how much of a terrorist somebody is. That would be the type of thing you would consider. I didn't really want to write an equation for this because very often you either are a terrorist or you're not, and that gives us a binary response as opposed to how much money somebody can borrow. How much money you can borrow is sort of a continuous variable. It can change by a couple $1,000 up and down, but it gets a little more complicated when you have a binary response. So, any questions on that? Was that response a little clarifying? Okay, thank you. Richard Bellman, a mathematician who, in the context of numerical approximation, invented the concept of the curse of dimensionality. And the curse of dimensionality basically means that in high-dimensional inference, the kinds of things that arise in the microarrays or the counterterrorism or things like that, statisticians are in real trouble because it becomes really, really hard to make any generalizable inference from the data that you see. Now, there are three nearly equivalent descriptions of what the curse of dimensionality implies. For a fixed sample size n, as the number of explanatory variables increases, the data becomes sparse and you're not able to do anything. That's one way of thinking about it. Another way is that as p increases, the number of possible models explodes. That's a second way of thinking about it. A third way of thinking about it is that in high dimensions, nearly all data sets are multicollinear. All of that sounds jargon-filled, but I think I figured out a way to explain each one of them. Let me imagine that we have one explanatory variable and one response variable. So you're a bank officer and you're trying to predict how much money somebody should get based on their salary. So there's only one explanatory variable. I have observations on 10 people. So I've got observations on a line. Perhaps 10 points on a line, and I'm trying to estimate how much credit they should get, and I'm going to fit some curve that says how much I think they ought to receive as a function of their salary. There I have one explanatory variable, one response variable, and I have perhaps 10 observations. Suppose I had the same situation, only instead of having just one explanatory variable, salary, I have some other explanatory variable, how many years they've worked for the company. Now I've got a two-dimensional surface of explanatory variables, and I'm trying to predict I have a two-dimensional surface of explanatory variables, and I'm trying to predict some function up on top of that that tells me how much money we can loan for them. Does everybody see the geometry on this? Okay. In that situation, if I have 10 observations, I have 10 observations here. 10 observations here are more spread out than 10 observations on a line. If you just think about where your fingertips would go if you put them down in a square as opposed to a line segment, they're closer together on the line segment. 3 explanatory variables, now I've got this space, and my 10 fingertips are distant in the 3-dimensional space. They're moderately close together in a 2-dimensional space, and they're brothers in a 1-dimensional space. So as you increase the number of dimensions of your explanatory variables, the same amount of data gets more and more sparse. It's not as concentrated in the explanatory variable space as you might wish, and that means it's very, very hard to figure out local bumps and dips in this surface that you fit. If you have a smooth surface and not much data, you can do okay. But if you've got a really bumpy surface that you're trying to fit, and you don't have a whole lot of near neighbor data, then it's very hard to find a local bump. Does that make sense to the gentleman in the red shirt? You're okay? Yeah. All right, good.
And he'll explain it to me.
It looks like a nice guy.
Use the term P. What do you mean by term P?
P is the number of explanatory variables. So it's salary, how long you've been in the work, how smart you are, things like that. And the response variable Y is how much money they're willing to loan you. A second way of thinking about this is the explosion in the number of models that you have to cope with. If you have P explanatory variables, the number of models that you need to think about increases very quickly. If you just think about linear models, you can have the model with just salary in it, the model with salary and how long you've been at work in it, the model with both of them in it, the model with salary, income, and what your grade point average was in college. There are a lot of different models that you need to consider. And as you think about all the different models, you need to have an ocean of data to distinguish one model from the other. If you're going to pick one model to use for the bank, and that model is one that you're going to apply for the next decade, and you're going to be willing to go into court and defend whenever somebody sues you for not giving them a loan, you have to have a whole lot of data to figure out which of those models you're going to use. There's a little calculation here that talks about how the number of models explodes in terms of the number of explanatory variables P. There's this sort of combinatorial explosion that means you wind up with a huge number of models increasing very, very fast in P. I don't think I'll walk through this example because I am a little behind the clock, but the main idea is that large values of P cause problems. I didn't think I was going to be able to say anything at all about multicollinearity, but on my way over here this morning, I think I thought about a way that might sort of explain it. Suppose we're being the loan officer in the bank, and I'm trying to fit, this is Abelard, this is Balthasar, Clytemnestra, Diotima, people like this all over the place. Diotima has a rich father, but she's not very smart. Abelard has a poor father, but he's pretty bright. That's sort of the way it works out. And the loan officer is now trying to fit a surface that comes out of here that says how much money they're going to give them. So out of the board here is the credit rating, and you're fitting a surface like that. Here, there's not much problem because I have smart people who are fathers are poor, smart people whose fathers are rich, and foolish people who have rich and poor parents. So this whole plane is pretty well defined. If, however, my explanatory variables were multicollinear, I'd have a problem. The way the world works, millionaires tend to marry millionaires, French poetry majors tend to marry French poetry majors. There's a lot of association between father's income and mother's income. So Abelard might have two parents who are both poor. Diotima perhaps has two parents who are both rich. It's rare that you find a family in which the father is super wealthy and the mother, you know, is a statistics teacher. So you wind up with strange things like that. So if I'm trying to predict how much money the bank is going to loan, this is the plane that the bank officer is going to fit from that linear regression equation. And the problem is this plane is only pinned down between my fingertips. Any rotation of the plane fits this data just about as well. Does that make sense? On this line, the plane is determined because I have a lot of data there. But up here and down here, there's no data. I don't have anybody with a rich father and a poor mother or the other way around. So this plane can rotate in lots of weird ways and still give me about equally good a fit to the data that I have seen historically. That's the multicollinearity problem.
But is that a problem unless you run into somebody who doesn't fall under the collinearity?
That is a brilliant question. And the immediate answer is if you only see people like the ones you've seen before, life is good. If you ever see somebody who's different, you're not sure what to do. And one of the not so obvious consequences of the curse of dimensionality is that in high dimensions, everybody you see in the future is going to be way different from everybody that you saw in the past. You're always working on the boundary of the information you've seen before.
You got that on the safe passengers, but not the one bomb.
It's like that, but it's even stronger if you think about looking at an individual's credit history. If we get lots and lots of information, everybody's credit history is unique. In some sense, everybody is an outlier in some dimension of their credit history. And that's why it becomes very hard to generalize in high dimensions. But that's an excellent question. The curse of dimensionality is intrinsic and very hard to get around. There are some things that you can do in sort of moderate dimensions. There are modeling assumptions you can make that will help you a little bit. Visualization is one of the coolest tools that allows us to do a little better than we might otherwise expect in these high dimensional cases. I'll start off just by showing you what a visualization of two cubes looks like. Here is obviously data on the edges of a three-dimensional cube, and the cube is tilted just a little bit out of plumb with the visual eye. So you can see each axis is rotated 10 degrees. This is a 10-dimensional cube, exactly the same kind of thing. Each axis is rotated 10 degrees, and you don't see any structure in that data at all. And in fact, there's a theorem that says in high dimensions, nearly all projections of the data look like just a blob of points. Which is why trying to do visualization in high dimensions gets really, really hard. You can look at it, but you won't see the structure. This picture has just as much structure as the one I showed you before, but here it's visible, and here it's not. And we've just gone from 3 dimensions to 10 dimensions. I'm going to talk about some of the nonlinearity stuff. Visualization is often closely related to smoothing issues. You have a batch of data here that are drawn, with random jitter from some smooth curve like this. And that smooth curve won't have any particular name. It won't have any well-established form. I was trying to think of something that would have this general shape on my way over here. And I imagine that you might imagine the number of friends you have as a function of age. The x-axis is off, but imagine that here you are in high school. You have friends. You go off to college. You have even more friends. You get married and have children, and suddenly you have no time to do anything for the next couple of decades. So you bottom out. You have no friends practically. Then your kids graduate from high school. They go off to college. You're free. You start to have more friends. Your life opens up a little bit. You don't have the stamina that you used to, so you don't have quite so many friends. But nonetheless, you have this weird function that describes how the number of friends you have changes over time. It's not a sine function. It's not a log function. It's not any named function. but it's a smooth curve. And I could go and I could ask a lot of people how many friends they have, and I might be able to get dots that represent, the sort of random variation you'd see. Some people are always a little more gregarious, some people are always a little shy, but over time you'll get a picture that might look sort of like that. In order to understand how this type of smoothing works, we focus on low-dimensional smoothing, and then we'll try and extend those ideas to high-dimensional smoothing. And it turns out that the simple ideas in low dimensions don't work so well in high dimensions, and it's the curse of dimensionality that's killing us. The smoothing stuff has been worked on by people for centuries. But one of the leaders in the 20th century was John Tukey, who was a famous mathematician and statistician. I understand that many of you are mathematics aficionados, so you probably know what's yellow and equivalent to the axiom of choice. Has anybody heard that joke, or am I just completely out of step? My teenage son warned me that I wouldn't be able to carry this off. Okay. You know the answer, David?
Oh no, if you were moving on, I was just going to say, so Tukey's also known for the word bit and the word software.
Yes, I was going to mention that in a minute, but I was trying to be intellectually engaging, and obviously I'm crashing and burning on that. Zorn's lemon is equivalent, is yellow and equivalent to the axiom of choice, and Tukey was the one who showed that Zorn's lemma was equivalent to the axiom of choice. But then he moved on and he started to do other things, and he became the godfather of smoothing in the modern world. But as David mentions, he also invented the term software and bit and other things that have entered the common vocabulary. If you look at the simplest type of smoothing, it's called bin smoothing. I'm using the data that I had 2 slides ago, the dots over here. What I'm doing is I'm taking the intervals between -1 and 0, and I'm plotting the average of the y values there. Then I take the interval between 0 and 1, and I plot the average of the y values there. And this gives me a bin smooth of the data. It doesn't look like the red curve at all, but it's a little smoother, a little more representative than what I had just with the dots. I can do something a little bit smarter, which is a moving average smooth. Instead of looking at fixed bin widths from -1 to 0, from 0 to 1, and so forth, I can imagine instead that I will average over 3 successive observations. So now I fix the number of points that I'm averaging, not the size of the bins that I'm using. That's a slightly different approach. It gives me a slightly, in some sense, smoother estimate of that red curve. Instead of fitting averages, I might imagine fitting lines to my data. So if you have sort of a smooth increasing curve, then fitting lines, fitting averages will give you a stair-step function, basically. If I fit lines, then I'm going to get something that probably tracks the curve's movement a little bit better. And here's what they call a running line smooth. And that has the type of properties that's beginning to look like a better version of the red curve than either of the 2 very clunky things I showed you before. And obviously you want to move on to even more sophisticated smoothers, because basically any 6-year-old with a tracing pen could do a lot better job for smooth than any of the things that I've talked about so far. And in fact, there are mathematically more sophisticated smoothers that get you curves like the green curve, that's a low S smooth, which looks pretty close to the red curve that we have. So in 1 or 2 dimensions, we know how to smooth things now. In higher dimensions, it's still very much of an open problem. Here is a third aspect of visualization, and I mention it because it is a success story from left field. It proves that anybody can make an important mathematical contribution, that not all of the low-hanging fruit is picked. Alfred Inselberg, back in 1985, came up with parallel coordinate plots, and I assure you that any 8th grader could have come up with that same idea at any time since Descartes first came up with the idea of Cartesian coordinate systems. What Inselberg was trying to do was to understand how you could visualize in high dimensions. With plots like this is a Cartesian plot. It's two axes at orthogonal angles to each other, and I can plot x and y on my plot. That's all very easy. If I'm a really good drawer, I can probably write sort of a three-dimensional plot. I could have sort of draw it in perspective and have an axis that's sort of diagonally coming out of the board. I can't do 4 dimensions. Nobody can really draw 4 dimensions very nicely in a plot. So what Inselberg suggested was that instead of trying to make the axes perpendicular to each other, or pseudo-perpendicular with this sort of diagonal perspective trick, let's just write each of the axes parallel to each other. So instead of having x1 and x2 like this, we're going to have x1, x2, x3 as parallel lines. And an observation, well here, I think this is Abelard, for example. Abelard had a poor father and a poor mother. So over here, on x1, father's income, Abelard has a low value. And then we draw a line to Abelard on the second axis. There again, Abelard has a poor mother. And so we have Abelard is an entire line segment that goes through this whole picture. So instead of representing points by lines, and instead of representing observations by points and axes by lines, we're now representing observations by line segments that connect the different axes. The woman, does this make sense? You understand what's happening here? Okay, so the nice thing is that I can look at 7 dimensions at once. I can say that Abelard, A, is low on x1, low on x2, low on x3, but considerably higher on x4, x5, x6, and x7. And what you see when you start looking at these higher dimensions is that you wind up with different kinds of structure depending on which variables you look at. Here in the UK, you have a card that you use when you go grocery shopping, and it indicates, you know, how many bottles of beer you buy, how many bottles of cheese, how many things of cheese you buy, how many diapers you buy, stuff like this. If x1, x2, and x3 are diapers and baby food and pacifiers, then what you wind up with is perhaps A, B, and C being single people, D, E, and F being people with children, and you see a sort of clear clustering there that the supermarket would be interested in. The supermarket would realize that, you know, you're the type of person who has 3 kids at home. You're probably going to be interested in bargain pricing on infant formula or so forth. As you move down here, you see that the clusters are changed. If these variables refer not to diapers and baby food, but perhaps to exotic, expensive cheeses and very fine wines and stuff like Belgian chocolates, these are rich people and these are poor people. And so you wind up with a totally different type of cluster analysis that is also important to the grocery store people, because they'll want to know, should we have a sale on Belgian chocolates, or will we get more money from having a sale on day-old bread? Yes?
Not to take credit away from Mr. Inselberg, but if you just stand this thing on the side, all you're doing is plotting one function, and plotting another function, and plotting another function. I did that back in the 60s.
It's not clear to me how the parallel coordinate plots allow you to look at all the different dimensions at the same time. Was that captured?
A function whose domain is 1 through 7, and that's your A function. You have another function whose domain is 1 through 7.
I
That's your B
don't think
function.
that's quite
histogram. People draw things like that with multiple histograms, don't they?
Let us take this offline, because I'm not sure that I have, you're probably right, but I'm not sure that I have completely apprehended what you're doing.
I'm certainly right.
Let me talk about another aspect of, a fourth aspect of visualization. And here we have data on, well, actually, I should go back here. There's a famous set of data that comes from olive oil. and one is looking at the chemical compositions of olive oil from, why is it slowing down? From many different parts of Italy. Here we go. This is a color-coded map of Italy that shows you the different regions in which high-grade olive oil is produced. And you'll see that there's sort of one family of olive oil that's in orange, another family of olive oil that's green, and it comes from Sardinia, and then you have some northern Italian olive oils that are in purple. And here we have a plot of those different olive oils. We're looking at two constituents of the olive oil, palmitic oil and palmitoleic oil. And as you can see, the purple stuff is a little bit more spread out, but the green and the orange are largely mixed up together, and it's sort of hard to distinguish those visually. If I could find a way to plot those in higher dimensions, here would be a parallel coordinate plot for palmitoleic, palmitic. I don't want the regions. Let me, well, the regions are categorical variables, and those were the groups that we talked about earlier. And if you look at it, you're getting a parallel coordinate plot that shows some clear separation between the oranges, the purples, and the greens. And in fact, if I go over here, turn this one off, turn this one off, turn this one on, 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 on. Being very slow. Now we've,
Still got region.
I've still got region. I was trying to kill that. That should do it. Okay, now what I am seeing here is that the different regions, they're often sort of tangled up together, but if I can look at all of the different constituents of the olive oil together, I'm beginning to see some clear separation patterns between the orange and the green and the purple areas. And that would be very useful if I were trying to do a blind taste test of olive oil or a blind chemical analysis of olive oil. I might be able to determine the region of origin by looking at the constituents with a pretty high degree of reliability. And on the famous international counterfeit olive oil market, I dare say that that type of distinction might be important to draw. A related issue is being able to do a rotating point cloud tour in high dimensions. Here again, I want to get rid of region and area, and I want to include these. Okay. Here I have point clouds in a 1, 2, 3, 4, 5, 6, 7, 8-dimensional space, I think. And by grabbing this with my pointer, I can swirl it around and look at things from different perspectives. And there are a few different perspectives, projections, in which you wind up with very clean separation of the purple, green, and orange groups. Those correspond to combinations of the 8 explanatory variables that absolutely distinguish the northern Italian olive oils from the Sardinian olive oils, from the South Italian olive oils. And that's a very important thing if you are somebody who cares deeply about olive oil. So that's an example of what you can do with visualization in high dimensions. And there are many other tricks. These are fairly lower level ideas, but they indicate that one can go a long way if the dimension isn't too high. Sadly, the interesting problems are ones in which the dimensionality truly is high, and one is faced with the daunting problem of trying to do important science when you just don't have enough data and perhaps too many dimensions to come up to really clear conclusions. And in those situations, there have been a batch of challenges. I need to expand this. There have been a batch of challenges, and there's been some progress that has been made. One thing that statisticians have been trying to do over the last few decades is to substitute computational power for mathematical calculation. Back in the distant old days when statisticians were few and far between and data sets were small, you'd sit down, you'd do a derivation to figure out the normal approximation for something, and you have a page of mathematics, not arithmetic, a page of mathematical derivation. And based on that, you'd be able to go off and make some statement to the scientist. The problems are so much harder today that you can't do an algebraic derivation of stuff. You have to let the computer somehow substitute computational power for human time. Another theme in the last few decades has been to provide interpretable models for complex data sets. It's really very unsatisfying to a scientist if somebody comes back and says, yes, we can predict the outcome, but our prediction doesn't make any physical sense to you at all. They don't like that. It's sort of like being the loan officer situation. If the loan officer from the bank comes back and says, we can't make you the loan, but we can't tell you why, then you go to another bank. It's not satisfying. And then lastly, we want to look at situations in which the number of explanatory variables, P, is very, very much larger than the number of observations, N. And none of these problems is fully resolved, but there's been progress, and surprisingly, often, as with the case of Inselberg, very simple ideas turn out to have a lot of mathematical legs. They can go a far distance, even without very deep work. Brad Efron is one of the people who worked on the first problem, which is trying to substitute the power of computation for algebra. And this led to the bootstrap. And the bootstrap is a simple enough idea that I am going to attempt to sort of wave my hands and explain what the issue is. There's some distribution of income in the UK. Probably has a long right tail because, well, no, it probably doesn't, but actually, there are not many billionaires. So it goes down pretty steeply. What you imagine here is you'd like to be able to estimate what the average income in the UK is, or the median income of a UK household. And people get antsy if you ask them this, so you can only get small samples. You might have 10 or 20 people who report their income, and from that you'd like to be able to estimate the median income in the population. Well, you can certainly estimate the median of the population. Your best estimate is probably something like the median of your sample. But you don't know how much plus or minus to put on that. If you say that the median income, household income in Cambridge is £25,000, would you be very surprised if the true median income was as high as £28,000, or would you be very surprised if it was as high as £30,000? How much plus or minus is reasonable to assign? And this is what statisticians do. We don't just give you the answers. Physicists can give you estimates. We tell you how certain we are of our answers, and that's the added value that we provide. In this case, the bootstrap is a way of taking your sample here. The numbers are, this is Abelard's income, £20,000. Balthazar's income, £40,000, and so forth. I have all these different people who have different incomes. I'm going to use the spread in the data that I see to give me some indication of how uncertain I am in the numbers in my estimate on the median income in Cambridge. And there's this little diagram here that tries to explain what's going on. And it's a poor diagram for the general audience, but I will try and explain it. F is the initial curve up here. This is the unknown true distribution of income, and we will never know what that is. Only God knows what the truth is. What we observe are Abelard, Balthazar, Clytemnestra, all of these people here, and what their incomes are. From that, I'm going to create I have a pool of data that I'm going to call F hat. And from that pool of data, I can imagine that I will draw new samples. I will draw at random from the data that I have. So I might get Abelard twice, Balthazar not at all, Clytemnestra 3 times, Diotima never at all, and so forth up through my entire sample. So and for that first sample that I draw, this set of Abelard, 2 Abelards, no Balthazars, whatever, I can calculate the median of that group. Then I can go back to my original sample and do a second random set of draws. This time I might not get Abelard at all, but I'll get Balthazar 5 times. Clytemnestra appears 3 times. So I'm going to wind up with a different set of samples. I can calculate the median for that second sample as well. I can do that over and over again automatically using a computer, and if I do that, I will wind up with a histogram that tells me how often my median income from a sample was 20, 21, 22, 23. I'll build up a histogram of how many of my second samples had medians that were as low as 20,000. How many of my second samples had medians that were as low as 21,000? I can build that histogram, and once I have that histogram, I can say I'm pretty certain that the median household income in Cambridge is around 21 or 22,000 pounds. Or I can look at it and say there's a whole big tail up here to the right, maybe it could be as high as 30,000 pounds. I'm using the ability to draw via a computer over and over again from my original sample to bootstrap myself up in order to have a better understanding of the total uncertainty in my estimate of the median income. Does that sort of make sense? That's about as hard as we're going to get today. That was the most extreme thing we have. It's a brilliant idea, and the important thing is you don't actually have to know a whole lot of high-level mathematics to work through it. In order to prove that it's a good idea, that requires work. But the key contribution, like Inselberg's contribution, doesn't require very sophisticated mathematical preparation. A second area has to do with finding interpretable models. And here, Jerry Friedman and Leo Breiman were leaders in the field. They wound up inventing, a number of things. They actually were incredibly prolific. But the cart tree is the one that they are most famous for. And this has been widely sold simply because it is so interpretable. You don't always trust it, but it's highly interpretable. One of their famous examples has to do with people who are admitted to emergency rooms complaining of chest pain. And it's very important for the physician to know whether or not that person has had a heart attack or whether that person just sort of ate too much spicy curry and is not feeling very good. So what you would like to be able to give the physician is a decision tree that allows them to classify people as to a heart attack situation or not. So the first question is the minimum systolic blood pressure over the initial 24-hour period greater than 91? And if it's not, that's a bad sign. The person has probably had a heart attack. So there you go down the right branch of the tree and you take appropriate steps. If, however, the systolic blood pressure has been greater than 91, then you ask, is this person old or young? Is the person older than 62.5 or less than 62.5? If the person is older than 62.5, then maybe, if the person is younger than 62.5, then they probably haven't had a heart attack. If they are older than 62.5, then you go left down the tree and you ask whether or not sinus tachycardia is present. If you go through this procedure, the physician is, one, able to make a preliminary diagnosis about whether or not the patient is a high probability heart attack victim or a low probability heart attack victim, and the physician can think about the quality of the evidence at each stage through that tree. It's in some sense medically interpretable, and people like that. These trees are grown basically through a search procedure. You take all of your data on people who had heart attacks and who didn't have heart attacks. You look at all of the stuff in their medical files, and you ask which variable does the best distinction first. And that best distinction first apparently, is whether or not the systolic blood pressure is greater than 91. After that, you look at all the people who had systolic blood pressure greater than 91, what makes the best distinction among those? And all the people who had less than 91, you do it the other way around. So you go through looking at your data at each step to try and build the best tree that you can, and that's actually not very sophisticated. Again, a bright 8th grader could probably figure that out. They might not be able to prove that it really will work. They might not be able to get the reliability estimates for something like that, but they would be able to think of the idea, and that's the starting point. I was going to talk a little bit about David Donahoe's work, but it turns out that he is here in the room today. So I'm afraid I'm going to have to pin the tail on the donkey, David, and allow you to say just a few words about your own work here. David has made enormous contributions to the problem of large P, very small n inference. Would you like to say a few words directly?
Oh, I'm giving a public lecture Monday, 5 o'clock, in which I'll talk about this in more detail. Basically, I was going to talk about the type of issue you started with, where you're setting up a predictive model. There are many applications where there are many potential predictors, and you don't know which ones to really use. So a bank may have a whole credit application with hundreds of descriptors about a particular case, and they know which loans in the past turned out well and which ones didn't. And they're trying to figure out which of all the things on the credit application help you predict. So often they're in a case, as you've said, large P, small n, where the number of data that they have in terms of previous loans in a certain batch is pretty small, but there's many potential predictors. So if you've studied college algebra, they've told you that it's crucial to have more equations than unknowns. And when you think about the implications of that, it would seem that you cannot do modeling where you have a relatively few number of loan examples as history and many more potential predictors than historical examples of loan. That's the same thing as having more unknowns than equations. And yet somehow empirical science and finance and so on manages to proceed. So it must be that college algebra is wrong in some sense. I was going to talk about how that could be and what it was that they didn't tell you in college algebra that they might have that would help you understand the situation. And it turns out to involve the geometry of what are called polytopes. You have an example of one there.
Yes. One of the key insights that David and his school have developed is that whether or not you can solve these equations depends on how many extreme points in a polytope are still extreme points when you project it to a lower dimension. And so the shadow behind that polytope is the projection onto a 2-dimensional space of a 3-dimensional polytope. And as you can see, some of the extreme points, like this one, are now interior in the shadow, and other extreme points are not. And that turns out to be crucial.
Is that here, you speak?
I think it will be in this room, won't it, David?
In this room, 5 o'clock Monday.
Yes, great. I am out of time, and I wanted to draw a few sort of obvious conclusions. Statistics is a wonderful profession because you get to work on anything. You can help bank loan officers, you can help historians, you can help physicists, you can help biochemists, you can help people who make olive oil. And so there's a whole range of applications, and our duty is to give good advice. Sadly, some applications are really hard, and there are limits on what type of advice we can give. The easy questions are largely solved. Research statisticians, PhD statisticians are working at the harder end of things, And some of those harder issues are ones that I've tried to lay out in today's talk. The Isaac Newton Institute is one of the leaders in the international effort among statisticians to provide data analyses, and these analyses are going to be transformative for medicine and manufacturing and finance, ecology, understanding global warming. That's clearly a very high dimensional problem. We don't understand it well yet. Some people may never understand it. So that's the reason why it's important to be able to do this type of stuff. The point I really want to make, because I was told there would be a lot of 14-year-olds in the room, is that you actually don't have to steep yourself in mathematics to make some kind of contribution. What you need is a fresh thinking, a different way of looking at it. You need to understand the problem and then have a good idea. And that doesn't necessarily require decades of mathematical study. And I've given, I think, 3 examples in which people who were sort of, not exactly amateurs of science, but people came in and they had an idea that was revolutionary, and it wasn't mathematically deep. So there's a lot of hope for everybody to be involved. But the bad news is, even after you've had this really wonderful, naive idea, you have to do a lot of mathematics in order to prove to the rest of the world that it's a good idea. Thank you very much.
Thank you very much, David. We do have time for just a couple of short questions. So does anybody, yes, right at the back there.
When you're doing your modelling in multi-dimensionals, how do you model for different weightings?
Yes. In the context of the bank loan officer,
Yes.
I imagine you think that your grandparents' income is much less important than your father's income, which is less important than your own salary. Is that the type of thing that
Yes.
you...
Yeah. So, for instance, your olive oil, which of the particular variables would be the greatest weighted, was what the question I was really asking.
For the olive oil question, it depends on what your response variable is.
Right.
If your response variable is how much you can sell that olive oil for, then your historical data ought to tell you which variables are the most important. And those are the ones that are going to receive high weights. If you find that olive oils that are rich in palmitic oils, well, those are the ones that have traditionally had the top values and the connoisseurs love them and so forth. Then that means that the amount of palmitic oil is going to have a very large beta on it. And so you get good prediction of the value. If, on the other hand, one of the other oils is not at all relevant, it's about the same for all of them, it has no influence, then the beta coefficient on that will be very close to 0 or very small. Yes?
The software you're using for visualization,
Yes?
what software was it?
Wonderful. GGoby software. Di Cook, Deborah Swain, and Andreas Buya developed it. Di Cook is one of the people who is here at the Institute, and I was hoping she was going to bring her 14-year-old son today, so there'd be at least one of them in the room. But no, it's freeware, it's wonderful stuff. You could start a consulting company tomorrow and do very nicely just by mastering GGoby. There's another question over here.
In the example where you were using GGoby, you had multiple dimensions represented in the grid and you were spinning around.
Yes.
How many dimensions can you usefully display using that technique?
If you are an athlete in this area, as Di Cook is, I wouldn't be surprised if Di could go up to 25 variables, maybe even more than that with a whole lot of work. Someone like myself, who is much less proficient, I find that 15 variables is about as many as I can sort of roll around and explore in these visualizations. So from my sense is that the real range of interest is from 3 dimensions up to 15, and there people can see good stuff. And above that, it requires serious work. And you can't go very much higher than that.
And do you normally, when you're dealing with, say, 15 variables, is it normal that you all find clusters, or does it just vary depending on the data set?
There's no good answer to that, but in my experience, when you have a complex data set that actually has scientific or commercial interest, there's hidden structure there. And so it's always worthwhile looking at it. If there's nothing there, then probably it's very hard to make any scientific progress or make a buck off of it. But if you're the first person to find the structure, then you're in good shape.
Thank you.
Right, well, I'm going to stop there. Thank you very much for the questions. Thank you very much to David. I'm just going to say before we finish, there's another talk, public talk this afternoon over in the maths faculty on the hidden mathematics of disease. And if these high-level lectures are blowing your mind, you can just play with all the mathematical toys that are in the central core over in the other building as well. They've got all sorts of fun things going right down to 5-year-olds there, and I promise you'll see 14-year-olds as well as 5-year-olds over there if you want to see some. So thank you very much to David. Thank you all for coming. Perhaps we can thank the speaker once again.